This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are discussing electrical analogy, conduction process in heat and mass transfer subject. The mathematical formulation for the heat transfer by the conduction process can be written as Q is equal to minus of K into A into dt by dx. That is the amount of energy that is flowing by using conduction process. Particularly, it happens in solids only. It depends upon the area of the cross section, thermal conductivity of the material, and temperature gradient, that is dt by dx. The integration of equation 1 for the wall of thickness is equal to L, and within the temperature ranges T1 and T2 under steady state conditions, then it can be written as Q is equal to K into T1 minus T2 divided by L. The modified equation of this equation is T1 minus T2 divided by L by K A now, where A is representing the area of the cross section, T1 is representing the higher temperature region, T2 is the lower temperature, L is the thickness of the wall or length of the object, K is the thermal conductivity of the material. The amount of heat energy that is flowing is given by Q is equal to K into A into T1 minus T2 divided by L now. So after modifications, this equation can be written as T1 minus T2 divided by L divided by L by K A now. This L by K can be written as now thermal resistance for the conduction process. So when we are modifying these equations, that the flow process of heat energy by using conductant energy with the flow of current, it can be written as now, here V1 is representing the voltage at higher end and VT is the voltage at lower end. The energy is, that is the current is passing from higher voltage V1 to lower voltage. Here R is representing the resistance of the coil now. So we can represent it here V is equal to I into R, I is equal to V by R now. So when comparing these equations with the conductivity of materials, that is heat energy flowing through the conductive materials, that 1 by R is representing, that is L by Kn. That is here now L by Ka is equivalent to, that is the R, that is the thermal resistance of the materials. So this is the relationship between the current passing through the coil as well as the heat energy flowing through the object, where V1 and V2 both are equivalent to T1 and T2. Resistance is equal to L by Ka. Q is that is thermal energy that is flowing, which is equivalent to the current passing. Okay, one problem which is related to this equation now. Determine the heat flow across the wall of 10 centimeters thickness with a constant thermal conductivity of 8.5 watts per meter per degree Kelvin when the surface temperature are studied at 100 degrees centigrade and 30 degrees centigrade. The wall is 3 meter per second, 3 meter square. Also find the temperature gradient in the flow directions. Here according to the figure now, the wall thickness is given now, the given data. Here 100 degrees representing the temperature at the higher end now, and T2 is representing the temperature at lower, that is here at this position now. L is equal to, that is the thickness of the wall, which is equal to 10 centimeter, which is equal to 0.1 meters. Thermal conductivity of the material is equal to K is equal to 8.5 watts per meter per degree Kelvin. Area of the cross section is equal to 3 meters square now. Therefore, according to the Fourier's heat law of conduction process, here we are having Q is equal to K into A into T2 minus T1 divided by length of the object now. So, by using these equations, Q is equal to R, it can be modified now. T2 minus T1 divided by L divided by K, L. L by K is known as the thermal resistance now. So, by using this equation, that is second equation, Q is equal to T2 minus T1 now, that is the difference of temperature. Here the negative gradient because the heat energy is flowing from higher temperature to lower temperature. So, 100 minus 30 divided by L is equal to 0.1 divided by K is equal to 8.5. Area is equal to 3 now. And substituting this equations, we got this value is equal to 17,850 watts. So, or it is equal to 17.85 kilowatts. Here, these equations, it can be written as now, that is Q is equal to, here we can take it as K into here T2 minus T1, that is known as temperature gradient, which is equal to dt. Generally, it is represented as negative only, divided by dx now, where length. The dt by dx is called thermal resistance now, that's a temperature gradient. So, according to this problem now, Q is equal to minus of Ka into dt by dx. So, yeah, from this relation, so the thermal resistance is equal to, we can write now, written as that is dt by dx, or simply we can write it now T1 minus T2 divided by L. This is also, we will get the same answer, which is equal to minus of 700 degree centigrade per meter. Or by using these relations now, we can take K is equal to, Q is equal to 17,850 divided by K is equal to 8.5, A is equal to 3. On this, by using this relation also, we will get the same equations now. So, this is known as the temperature gradient of given object. So, sometimes this is also called here now thermal resistance. The values of here dx divided by Ka is called, okay, from this relationship we are having, that is L by Ka is called thermal resistance. Here conductions now. Conduction is the heat transfer which is taking place particularly in solid from higher temperature to lower temperature. The amount of heat energy that is flowing, it depends upon thermal conductivity of the materials, area of cross section, the temperature difference, and inversely proportional to the thickness of the slab or the slab. So, the rate of equations, that is the rate of heat transfer, generally it is measured by Fourier's laws of heat conductions. It is given by Q is equal to minus of Ka into dt by dx now. Now, we are comparing these equations with the electrical flow of current. So, these equations, it can be written as now, that is Q equal to K into A into T1 minus T2. This equation, it can be written as now T1 minus T2 divided by, here it can be written as T1 by T2 divided by L divided by K into A now. This L by K A is known as thermal resistance now. T1 minus T2 is known as temperature potential now. Now, consider an electrical circuit having the resistance R, and electric potential A1, A2 as represented here now, having a resistance R. The flow of current I is given by I equal to E1 minus E2 divided by R now. That I am comparing these two equations, they are having the relationship between flow of thermal energy as well as the flow of current now. That is, I am comparing that E1, E2, what are the, you are taking potentials at one end, T2 is represented other end. They are equivalent to the T1 and T1 and T2, that temperature at one end 1 and T2 is represented temperature T2. And the resistance, electrical current resistance, which is equal to the thermal resistance, it can be represented as L by K A now. If an object having here the heat energy flowing, here I am taking this one more object now. If L is nothing but representing the length, and T1 is representing T1 at one end, T2 is representing T2 at the other end now. The energy is flowing through this slab or the bar, assume here taking place by using thermal conductivity. But here the T1, the surface of the object which is having higher temperature, is exposed to hot fluid, which is having temperature is equal to T alpha, and H is representing the convective coefficient of hot fluid, H naught. Similarly, the T2, that is the temperature at the other end is the T2, which is having contact with the air. That means TA is representing the temperature of atmospheric air. That means the heat energy is flowing here now from hot fluid which is having temperature T alpha to atmospheric air having temperature TA by using conduction process, that is by using this through the wall now. Then according to the flow of energy from hot fluid to the air by through the materials is given by the equations Q is equal to T alpha minus TA divided by 1 by HIA. Here HI is representing the at inlet position, it is having thermal convective coefficient of heat transfer HI. A is representing the area of cross section plus L by Ka, where L is representing the length of the object, K is representing thermal conductivity of the materials, A is the area of the cross section plus 1 by again now H naught A, where H naught is representing the that at outside, that is here now, that is the convective surface of two air, these equations. So this is a flow of energy at 3 stages. One is a here convection process taking place from hot fluid to the object. The second one is conduction process which is taking place in the slab. And the third one is again convection process which is taking place from outer surface of the object to the atmosphere. So when comparing this process with the electrical analogy, we can take it as T alpha is representing the temperature at higher end, Ti is representing temperature at the of atmosphere now. So 1 by HIA is representing the thermal resistance of the convective surfaces at the inlet. L by Ka is representing the thermal resistance of conductive materials, and I 1 by H naught A is representing the again convective thermal resistance. That means from the outlet to the atmospheric air. Similarly, when it is having just 3 slabs here given now, 1, 2, 3 blocks are given. The heat energy is flowing from the air hot fluid, which is here maintaining at T alpha to outside, that is nothing but here Ts, just by using the composite walls. That means it is made up of 3 different materials, which is in the form of layers now. That is the 3 layers, which is represented here now. First layer, second layer, third layer. Let T1 is representing the here now temperature at the hot surface, which is having contact with the hot fluid. T2 is representing the temperature at the junction of first and second slabs. And T3 is representing the temperature between the second and third junction of second and third blocks. And T4 is representing outside now, that is outside of the composite wall. From T4, the energy is flowing to the atmospheric air, which is represented as T alpha naught or Tn naught. So according to the heat conduction process, the amount of energy flowing from T alpha to Ta is given by T alpha minus Ta divided by 1 by HIA. It is representing the thermal resistance of the art fluid to the surface of the object which is exposed at a temperature of T1 plus L1 divided by Ka where L1 is representing thermal conductivity of the first block, Ka is representing thermal conductivity of first block, A is representing the area of the cross section. Similarly, L2 is representing the thickness of the secondary materials divided by K2 A2 plus L3 divided by K3 A3 plus last one is again that is the thermal resistance for the convection process 1 by H0 to A naught. And representing these equations with the electrical analogy, we can write as T is representing the inlet temperature which is having higher temperature T alpha, and Ta is representing atmospheric air. Now at the junction, this is nothing but T1 is represented already we discussed. It is the surface which is having contact with the art fluid. Now T2 and T3 it can be represented. So this is the relationship with the flow of thermal energy with the flow of current through the different types of conductors. One problem just we are taking based on electrical analogy. The wall of heating unit in a cool region comprises 3 layers of 10 cm outer brickwork having K is equal to 0.75 watts per meter per degree and 15 centimeters, 1.5 centimeters inner wooden paneling. K is equal to 0.75 watts per meter per degree and 8 centimeters intermediate layer of insulating materials. The insulation layer is stated to offer resistance to twice the thermal resistance of the brickwork. If inside and outside temperature of the composite walls are 30 degrees centigrade and minus 10 degrees centigrade respectively, determine the rate of heat loss per unit area of the wall and thermal conductivity of the insulating materials. So here and the solution is the thermal resistance for the plane wall of thickness delta, area A, thermal conductivity K is prescribed by the relations RT equal to delta divided by K A now. So from this relations, the total heat energy that is flowing through the blocks of different layers, that is from higher region which is exposed to 30 degrees to minus 10 degrees, it can be represented as Q is equal to T alpha minus Ta divided by L1 Ka plus L2 divided by Kb plus L3 divided by Kc. Or according to thermal, it can be represented as T1. The first resistance is offered by for the fluids which is flowing from art fluid to the surface. The second one is the first block to second block and third block. Here now L1 divided by K1 A1, L2 divided by K2 A2, L3 divided by K3 A3. The resistance of brickwork is equal to RT1 is equal to, we are having equations which is equal to K divided by, which is equal to here now L1 divided by Ka AA. By using the relations now 10 into 10 to the power of minus 2 divided by 0.75 into 1 now. From this relationship we got it is equal to 0.133 degree per watts now. Similarly for the wooden paneling now it is equal to 1.5 into 10 to the power of minus 2 divided by 0.133 into 1 which is equal to 0.1128 degree per watts now. The resistance of insulating materials is equal to RT1 is equal to We are having 2 into 0.113, which is equal to 0.266 degree per watts now. The total resistance is equal to sum of the resistance offered by the brick, wooden paneling as well as the insulating materials, which is equal to the 0.5118 degree per watts now. So according to the heat loss is equal to change in temperature divided by the thermal resistance, which is equal to 30, change in temperature to 30 minus 10 divided by 0.5118, which is equal to 78.115 watts. The thermal conductivity of the insulating material is equal to K is equal to, we are having equations, so delta divided by Ka RT. From this relationship we got 7.5 into 10 to the power of minus 2 divided by 1.05118. From this relationship we got it is equal to 0.1465 watts. So this is the answer. Here it is equal to degree per meter now. Now the problem 2 now. A furnace wall is made up of a steel plate 10 mm thick, that is the K is equal to 62.8 kJ per meter. Okay, these are the reference textbooks as well as the prescribed textbooks followed for collecting the materials. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.